Hello everyone, thank you for attending this presentation. Today, me, Mohamed Amin Merso, and Vincent Brochu, Gabriel Laberge are going to present the article Adversarial Examples in the Physical World. Presentation plan is the following. First, we're going to introduce the adversarial examples, how they are generated, and how do they transfer. Then we're going to dive into generation methods like basic iterative method, iterative least likely class method. Then we're going to see the application of adversarial attacks in the physical world and some countermeasures before concluding our presentation. First, I'd like to ask you a simple question. What do you see here? You can quickly answer in the chat. While some of you might see a school bus, temple, or a dog, AlexNet only sees an ostrich, une autruche. This is because these are not simple images. These are adversarial examples. Adversarial examples are normal inputs which small and imperceptible perturbation is added in order to mislead the model into classifying it in the wrong class. In a normal machine learning setting, we would train our model on training data and then deploy the model. When given normal inputs, the model would give correct levels. But in an adversarial attack, the attackers tries to perturb the data, add small and well-computed perturbation in order to generate adversarial examples that are misclassified by the model. For example, in the detection setting, an attacker could evade detection by slightly modify the features of its data. Back to our examples, we can see from left to right the normal image, the perturbation, and the adversarial example. It is very hard or even impossible to distinguish the adversarial example from the normal image. The generation of adversarial example is a minimization problem where we try to minimize the distance, in this case, the Euclidean distance, between the adversarial example and the normal example, so that they are as close and as similar as possible. And we also try to minimize the loss function between the adversarial example with regard to the targeted class, which is in this case, the ostrich. Fast gradient sign method is a fast method to generate adversarial examples. It uses the gradient of the loss function. We all know that to train neural networks, we use the gradient of the loss function that we propagate back in order to update the parameters. What fast gradient sign method does is that it propagates the gradient back to the inputs and then uses the sign of this gradient in order to update the inputs and create an adversarial example that is as far as possible from the true level. So it adds the sign of the gradient multiplied by the perturbation, which is xn. In a targeted way, we could optimize the inputs in order to achieve a specific targeted class. And then we would optimize the input in order to achieve this adversarial objective. This is the famous example of a panda that with a small perturbation computed by FGSM is now classified as a given. Two interesting things here are first, the perturbation doesn't really mean anything to the model. It is classified as a nematode with 8.2 confidence. But even more interesting, the normal example was classified as a panda with less than 60% confidence, while the adversarial example is now classified as a given with more than 99% confidence. Not only we will be able to misclassify the example, but the neural network is now even more confident in its prediction. So some might say, okay, we can generate adversarial examples and then we can fool models, but anyway, my model is secret, my parameters are secret, and even my training data is secret. How can anyone generate adversarial examples against my model? Well, studies have shown that adversarial examples generated for a specific model could transfer to other neural networks that were trained on different data. Even more, this heat map shows that adversarial examples generated for different models could transfer to different types of models. For example, neural networks, SVMs, decision trees, or even ensemble learning.
Now that we have defined adversarial attacks and shown an example on a panda picture, well, let's take a step back and go through the math of how to compute these attacks. We're going to work with an epsilon ball to define our neighborhood. So basically, the attack must be part of the set of all images such that the distance using the infinity norm between the perturbed image and the original one is smaller than some epsilon. Here, the infinite norm is just the maximum difference between each individual pixels of the images. For example, if we work with only 2 pixels, so 2 dimensions, each image can be seen as a point on the screen. Now, we're going to refer to the original image with a diamond shape. And here the neighborhood is a square around the instance. And the width of the square is 2 times epsilon. The main assumption of the FAST method is that the cross-entropy loss is linear inside of this hypercube surrounding the image. Here, plotting the level curves of such a linear function, we see that if we want to maximize it inside this neighborhood, we are obviously going to end up at one of the 4 corners. Basically, this justifies using the sign of the gradient to get basically the direction, and we go an epsilon step in each direction to end up at one of the corners. And this generalizes to higher dimensions. However, the assumption that the loss is linear is a very strong one, and it's going to be relaxed. Now, the method introduced in the paper is called the basic iterative method and consists of making multiple small steps instead of making one large step in this epsilon ball. Now we start our adversary is the original image, and then we iteratively update it using, once again, the sign of the gradient, but times a learning rate alpha, which is typically smaller than epsilon. Going back to a 2D example, instead of making one large step, we're going to make multiple smaller steps to end up at the maximum of the loss function. Note here, we do not assume linearity of the loss function. We have a problem. Our adversarial images must be part of some feasible set, which is the intersection between all possible images and our neighborhood. Going in 2D, the set of all images is the big square, and the smaller square is the neighborhood. Now, the intersection between these 2 sets is the set of all possible attacks, well, at perturbed images, I should say. But we need to make sure that when we update our adversary, well, we're still in this set. So we use an algorithm called projected gradient ascent, where we have a half step, which consists of using the sign of the gradient to update our image. And then we compute, we find which element in the feasible set is closest to this updated adversary. And this becomes our true adversary after one step of projected gradient ascent. Visually, we have one update. Oh, we go outside of the domain. And then the projection step is going to pull us back toward the domain. And we pick the point which is closest, which is this one. Well, the one pointed by the second arrow. In the case of the method in the paper, the neighborhood is very simple. It's the intersection between 2 hypercubes. And hence, the projection has an analytical solution. In the paper, this projection is referred to as clipping and has this very complicated formula. It's not easy to understand what happens in this formula at first glance, so I really suggest to think of it as a projection. And now the intuition is clear. So we see the iterative method, we update the image, and then we clip it, update the image, clip it, so on and so forth, until convergence. A second contribution of the paper is a targeted attack called iterative least likely class method. Now we're going to choose a target class, which is going to be the least likely class according to the model. So looking at the output of the softmax units, we pick the one with smallest probability, and this becomes our target. For example, This class could be a car if the original image was a panda, for example. And now we do a targeted attack where we, once again, we iteratively update the image, but now we try to minimize the loss with respect to our target class. So we want to perturb the image in a way that it becomes classified as what we want. Here are some results on ImageNet, where the authors use Inception with the Inception v3 network. Now the clean images are shown as a reference, so they reach 80% top one accuracy on this data set. And they also show the results of attacks using the FAST method, the basic iterative method, and least likely cast method, which were both introduced in the paper. And note that these attacks were done with multiple values of epsilon. We're only going to consider values of epsilon smaller than 16, because if we go above 16, then the perturbations are visible to the naked eye, and this goes against the whole point of attacks, which must be stealthy. Looking at smaller values of epsilon, we see that both methods introduced in the paper are more effective than the FAST method to fool the network.
Being able to generate images that fool a neural network is impressive. But what if your only input method is through the physical world by showing an image to a camera? Are the adversarial perturbations too subtle to be preserved when seen through the sensor of a camera? Are some methods of generating attacks better suited for the real world? And what kind of transformations are more likely to destroy attacks? To evaluate attacks in the physical world, we have two tools. First is the accuracy of the classification, and second is the destruction rate. The equation of the destruction rate might look a bit complicated, but the intuition behind it is very simple. It's the fraction of attacks that would normally succeed on photos that were originally classified correctly, but failed because of a transformation. We have the original image, the correct category of the image, the adversarial image, and the adversarial image after a transformation. For each of those images, we ask three questions. Is the original image classified correctly? Is the adversarial image classified incorrectly? And out of those images, is the adversarial image now classified correctly after the transformation? The lower the destruction rate, the better the attack resists transformation, and a destruction rate of 0 would mean that the attack always succeeds even after being transformed. So what is the real-world transformation? Here's the experimental setup used in this paper. First, you generate a printout with clean adversarial images and a QR code in all four corners. You convert this printout to a PDF and you send it to a printer. Then you take a picture of the printout with your cell phone camera. You use the software to align and warp the image back to its original shape using the QR codes, and you crop out the picture, discarding any printout where the QR code recognition failed. Using this setup, there are 5 factors that have the potential to destroy adversarial perturbation and ruin the attack: the printer scaling, the printer resolution, the camera noise, the camera angle and the warp correction, and the lighting conditions. Using these images, we can create 2 datasets. The average case where the attacker tries to cause an image chosen randomly to be misclassified, and the pre-filtered case where an image set is created where all images are correctly classified with an 80% confidence, and all adversarial images are incorrectly classified also with an 80% confidence. The pre-filtered case simulates a situation in which the attacker can select which image to attack, and only attack an image where he knows the adversarial modification already worked well. It's also important to note that in these experiments, the attacker has access to the model parameters and architecture of the neural network. Let's look at the results. Before transformation, we can see that attacks generated with the FAST method have a higher accuracy and perform worse than attacks performed with one of the iterative methods. But when we look at the real world, we can see that the trend reverses and that now attacks generated with the FAST method have a lower accuracy than attacks generated with one of the iterative methods. This means that the FAST method is more robust to transformation. If we compare the FAST method in the average and pre-filtered case, we can see that by removing the images where the FAST method performed poorly, we can improve the performance in the real world and decrease the accuracy even further. For the iterative methods, the result is the opposite, which is a bit counterintuitive. But this is explained by the iterative methods making very subtle co-adaptations in order to increase confidence, and that those changes are not very robust to the photo transformation. When we look at the destruction rate, we can see that the fast method with large adversarial perturbation performs very well, with most images still being misclassified after being transformed. For the iterative methods, the results are worse, and we can see that even with large perturbations, more than 40% of the images stop being misclassified. You might now be wondering what happens if the attacker doesn't have access to the model, but as we've already mentioned, attacks are often transferable from one model to the other. Here's an example of a black box attack against a TensorFlow camera demo app, where the washer image is easily misclassified into a safe with only small adversarial perturbations using the fast method. Now that we've seen attacks in the real world, we can also look at transformation in a more controlled way by using an image modification software. The following transformations were tested: a change of contrast, of brightness, Gaussian blur, Gaussian noise, and JPEG encoding. When looking at the brightness and contrast, we can see that the effect is very low, with a destruction rate between 5 and 20% at most, depending on the attack method. The blur, the noise, and the JPEG encoding have much more significant effect, and the destruction rate can reach 80 to 90% for iterative methods, and we can also see that the fast method still performs better.
Now that we've seen gradient-based adversarial example generation methods, let's see what other types of methods exist. The Jacobian-based silence map attack is a method that uses the Jacobian matrix, which is the gradients of the outputs with regard to the inputs, and then builds a silence map in order to select for a targeted class the feature that has the bigger impact on the classification, and then perturbs only these features. This method is iterative, so we will choose a feature in each iteration until we reach the adversarial objective. Deep pool is more a geometric method, where we try to find the shortest distance between the normal example and the classification boundary it has to cross in order to be classified in another class. This distance is the perturbation added to the example. And finally, Carlini and Wagner's attack is based on the optimization of this problem. It uses optimization algorithms like Adam in order to minimize the distance between the adversary example and the normal example. And it adds also an interesting objective function that it has to minimize in order to achieve the adversarial objective. In the paper, the authors propose several objective methods. Well, is it such a big deal that we can misclassify images or even voice, or is it a real danger for society in general? Well, let me tell you about something I really like, which is street art. In Montreal, you can see on a traffic sign people drawing funny things. But what I don't really like is this kind of street art. This is an adversarial sticker that has been carefully computed in order to misclassify the traffic sign as a speed limitation by image detection models. So if I were you, I would consider adversarial examples before buying a Tesla or before even crossing the road. But what do we do now? Is machine learning completely broken? Should we just abandon machine learning and machine learning courses? Well, no. Hopefully, there are some defenses that exist against adversarial examples. There's a very well-known adversarial retraining, where we try to augment the training data with adversarial examples and then retrain the model on this data. There's the adversarial detection, where the purpose is to analyze the input before feeding them to the model and detect the adversarial examples. And there's also the network distillation, which is a method to transfer knowledge from bigger network to smaller network. The original purpose is to reduce the variance, but it has shown good results for adversarial examples also. So as a conclusion, we've seen that despite their performance, neural networks are vulnerable to adversarial examples. We've seen how to generate adversarial examples and how do they transfer from different models. Also seen that adversarial examples can be implemented in real-world scenarios, for example, the traffic sign. Hopefully, there is an active research trying to find new attacks and new defenses in order to robustify machine learning models. But what we have to remember is that adversarial examples are just one category of adversarial machine learning. There's a lot of other attacks, for example, poisoning, which happens on the training data, distraction of the parameters, or even inference and other types. We have seen during this presentation the adversarial examples and perturbation applied to unstructured data, like images. But what happens when the data features have a constrained structure? What happens when we work on meaningful features? We can no longer just apply a random perturbation to generate adversarial examples, and we have to take into account the semantics of the features. This is my research project, so if you ever have questions on this. Well, thank you for your attention. Now